Can you all see the whiteboard?
Yes, sir.
Yeah. So shall we begin? So essentially what I was trying to tell you is that there is this whole principle of, so quickly to revise what I was doing was that um, this whole basic, the premise is rather simple. E plus S is equal to ES, and this is the essential principle we will use all the time, is E plus P. And as I said that if I do just this part and use the concept of fractional saturation, then I have a very easy formulation which is given by Kd is equal to, the dissociation constant is equal to E into S upon ES, and using this and the essential principle of the total enzyme being partitioned into two groups, E plus ES. The enzyme is partitioning into two sections. We can then derive the basic functions. The more correct and the more accurate method is to say that d of ES by dt is equal to 0, which is steady state of ES, and then this becomes obviously equal to K1 into E into S. I will just write E dot S, so it's easier that way, minus K minus 1 E in ES. And then, of course, the third term, now this was equal to 0 by this method, essentially. But now we have another minus K2 term into ES. So, oh God, this started very early. This problem started very early. Can you still hear me? And when we add this term, this is called the, can all of you hear me?
Yes, we can.
Yeah, yeah. So whenever I switch it off, you should say we are still able to hear you. Oh my, this is every second now. This computer is going bad truly fast. This is called the Briggs-Haldane relationship. This is called the Briggs-Haldane formulation, the Briggs-Haldane equation, and the Briggs-Haldane equation is slightly better. So this formulation and is called the Briggs-Haldane equation, and it brings about a slightly different formulation, because we can now, I mean, instead of writing ES is equal to, we have to write K minus 1 plus K2. So instead of K1, we have to write K minus 1 plus K2 into ES, okay, is equal to, K1 is equal to K1 into E into S. I hope you realize this, right? And then, of course, some of you did this and some of you did not do this, but we can write this as K1, and E can be written from this total material balance as ET minus ES. This is one way to do it, okay, into S. All of you following this? And then I leave the algebra to you. This is E into S, remember, and this is ES. So you have to make this distinction. So really, this is one basic equation, but remember that we also did one more very important component which I sort of missed out, but I should say this actually just for the sake of completion. Remember, we are doing enzyme kinetics. Unlike biochemists who are doing enzyme binding studies. The difference between enzyme kinetics and enzyme binding studies is that in enzyme binding studies, we use a very large amount of enzyme and a proportional amount of substrate. How does the enzyme bind with this? This is the kind of study which I am not going to talk about. We are not going to study this. We are only studying enzyme kinetics. And what is the difference between these two principles? Is that in enzyme kinetics, the substrate concentrations are very, very high, because we add a very small amount of catalyst. And so therefore, theoretically, S is much larger than the ES, because substrate concentration itself is, so the S, when it binds, S does not partition between free substrate and bound substrate. So S for all practical purposes is S free. See, remember we said that because the enzyme binds, it partitions into two components, right? And therefore the enzyme, and this is the part of the enzyme which is in the active state and where we calculated fractional saturation from ES divided by ET. But for substrate, this approximation applies as far as when we are doing enzyme kinetic studies. And so you have to be cautious when you are doing enzyme binding studies where the amount of enzyme is so large that the substrate concentration also declines. So you have to set up the similar balance on substrate as well. But you know, we are not going to do that, but you have to keep this in mind. And obviously you remember by a little bit of algebra here on this equation here, the Briggs-Haldane relationship, or actually here, we can actually get the value of ES in terms of ET, which is what we were trying to do. Which was, what was it? K1, we did it yesterday. K1 ET into S divided by K minus 1 plus K2 plus K1S, right? K minus 1 plus K2 plus K1S. Right? Okay. And of course, as I said, that the velocity of the reaction is nothing but K2 into ES, where K2 is also called the Kcat. I hope you now realize that when ES is almost equal to ET, you get the maximum velocity. That is what I was telling you. Then K2 into ES can then you simply multiply this by K2 here, and you will get exactly the same kind of formulation of V is equal to of, and you can multiply this by K2 into ES, and you can see that ES is equal to this. So V becomes equal to this into K2. And then you can see that again K2 into ES becomes Vmax, K2 into ET, sorry. Vmax becomes K2 into ET. Here, this into ET. And so we have the velocity of reaction. I mean, I'm sort of revising it quickly, and I should maybe, if all of you are not following, I can do this algebra. It's much simpler. Km plus S. This is the formulation that we get again, even using the Briggs-Haldane equation. So this is a quick revision of what we did. You remember all this? All of you?
Yes, sir.
Yeah, so this algebra you can handle, and you can now find out what is Km. It is no longer the dissociation constant, but it's actually K1 upon K1 K minus 1 plus K2. So really the formulation is very simply speaking, and you can see this very obviously. Oh, I rubbed out the wrong one, but if I rub this out, then this formulation here is actually now V is equal to, come on, let me hear you out so that I know what it is. K2 ET into S, I rub that one out, so, and then Km becomes what? It is no longer K minus 1 upon, sorry, it is no longer K minus 1 upon K1, it is K minus 1 plus K2 upon K1, right? Plus S. Okay? So the Km value here is this instead of K minus 1 upon K1. That is the only difference. And K2, as I said, is the catalytic constant, Kcat. K2 is here, K2 here is actually called the Kcat. And as I told you in the last class, so that you know, it is Vmax, it's K2 upon Km, which is really the critical thing because substrate concentration is very small and most reactions are first order. But the point that I'm trying to make is that this part here, Briggs-Haldane is also used because, I'll rub this out, and it's all that, because if you plot substrate concentrations and you plot hear me all of you with respect to time, now really the substrate concentration is going to decline with time, right, like this, because it will not go slowly, it will sort of start tapering down, and product will start looking like this. I should match actually, sorry. Molar concentrations here, and the enzyme and the ES, which are very important. The ES is, that is the critical point. The ES, here there is a very quick rise, and this time is in nanoseconds. So I told you about the relaxation time kinetics, that this is ignored. The time it takes for the substrate enzyme complex to stabilize, that also is a time. So there is always a start of the reaction where the product formation actually did not happen like this, but started happening like this. And this fall actually was like this. So this small thing we ignore, because this is the time which is so small compared to the actual kinetics, is that we can safely ignore it using the relaxation time principles, that the time constants for binding are very, very short. And so it reaches steady state, it reaches equilibrium. Because things which are fast reach equilibrium, things which are slow are stuck in the initial state, according to the. So your window of observation is for this whole thing. So these times can be safely ignored. And we come back to this point that ES actually is almost a steady state, till actually the sort of experiment ends, when it goes down. And therefore, for all practical purposes, because binding is very, very efficient, the E values, the E is actually almost always zero. Of course, it starts like this, but that's a very short period, and it is almost like this, because most of the enzyme is bound, very little enzyme is free, because substrate enzyme complex is very, very favorable, and only when it ends, sort of, it gets free. So this is the window of my observation, and so this is steady state, this is rising, this is falling, and this is a steady state. So all the assumptions are essentially valid, right? So you can make out from this two very simple points, that if we plot velocity versus enzyme concentration, this is a straight line. ET. So as we increase ET, our velocities keep on increasing, especially the initial velocity. That is why in the lab practicals I was saying that if you are looking at enzyme kinetic data and you're trying to not have the effect of S, you need to do it for very short time periods, so that the initial velocities are found out. It is this velocity, the dp by dt associated with this slope, that is important. So you can do it for this long, you can do it for this long, but beyond this, if you do take points here, if you take such long time points, you will end up with a wrong estimate of velocity. The dp by dt will be like this. So you want to do it for long enough, but not too long. Or similarly, ds by dt, you can take the slope here. And these slopes are matching. So the initial velocity is versus total amount of enzyme will show a straight line, because substrate is very high. And so what is the elasticity associated with this? So what is the elasticity of what is EV by ET? That's equal to, hello?
1 year.
1. So this is 1. You waited so long that the computer stopped working. So this is 1. So this is 1. But and of course you all know the other graph, which I don't even want to talk about. We have already heard this. V versus S plot, which is like this. And the equation, of course, is V is equal to V max S. We are repeating ourselves, but for the sake of completion, Km plus S. And this here is V max, the maximum velocity at saturation substrate concentrations, and half of V max is this value here is Km. You're all familiar with this, right? And of course, the fractional saturation, now we go back to fractional saturation instead of Briggs-Haldane, and the fractional saturation is given by, what was the fractional saturation? ES by
V max.
ET. By ET, which interestingly, as you rightly said, is also equal to V by V max. isn't it? This is the amount of things which are saturated. This is the total amount of enzymes. So the fractional saturation is ES by ET, which is also equal to Vmax upon VA, V upon Vmax, which therefore by the simple algebra becomes also equal to which also becomes equal to S upon Km plus S. Correct? So the elasticity, now you know the elasticity of this equation here. What is the elasticity of this equation? EV by S kya hai? We derived it in the class. What was it?
Km by Km plus S.
Km by Km plus S. So you can see that the fractional saturation is this and the EV by S is this. So very clearly you can see that what is the relationship between the two? E V by S is equal to 1 minus fractional saturation. So you see the beauty of these two concepts coming together. That on the one hand, when fractional saturations are very small, clearly a lot of enzyme is unbound. There is very little ES and a lot of ET. So when I increase substrate, then because there is very little S, so the amount. So when I increase substrate concentrations, then this equation here tells me something which is very obvious conceptually, which is that as my substrate concentrations are low, at low substrate concentrations, as I increase substrate concentration, as I increase S, fractional saturation is close to 0, then EV by S is equal to 1. And when it is completely saturated, additional substrate is not going to help. It is not going to increase the rate of reaction, so EV by S is 0. So high substrate concentrations, high saturation, impact of substrate concentration is negative, 0. Very low substrate concentrations, you increase the substrate concentration slightly, immediately the enzyme picks it up, and therefore EV by S is 1, because you know the elasticity with respect to substrate is 1. You add more substrate, the proportional increase in substrate is proportional increase in velocity. Because EV by S is nothing but the fractional increase in velocity upon the fractional increase in substrate. So this response is absolutely proportional to 1, equal to 1, when there is no saturation. And that is very obvious from this graph as well. Because you can see that here the slope upon V by S, and here you can see the slope is 0. So all these are captured together. And as I was telling you in the last class, that it is important for you to remember that okay, not clear, can eraser. Let me sort of rub this out. So this you keep in your mind for some time. And so as I was telling you in the last class, that for all practical purposes, most cellular reactions take place at low substrate concentration, low S values, because substrates are not allowed to build up inside the cell. And so therefore really what we are looking at is V is usually and as the biochemist will say, K cat instead of K2, K cat E total S upon Km. Right? Okay, and so the amount of enzyme, as I said, by definition, you all know that by definition, the EV by E is equal to 1. I just now showed it to you. EV by S is also equal to 1 at this point of time, because this is the rate constant. It is actually equal to Km by K cat by Km into ET into S. So it's first order with respect to ET, it's first order with respect to substrate. And so very large values of this would make the enzyme extremely efficient. Very small amounts of enzyme and it can still convert substrate. And as I said, that enzyme has to see the I think I will have to complain to them. That here is the enzyme and this is the pocket where the substrate sort of binds and the substrate has to diffuse, and typically the maximum value has to be greater than the rate of diffusion. Sorry, smaller than the rate of diffusion. And what are the typical diffusion constant values? Do you have any of you have any idea? Unlikely. It is approximately 10 to the 9 units m-1 second minus 1 most. And there are relationships where this catalytic efficiency ETAS is also of the order of 10 to the 8 plus. Greater than. So you can see that actually such enzymes are actually more or less diffusion controlled, because it's very unlikely that evolution would have made enzymes so efficient that they are faster than the rates of diffusion. I mean, there's no need, because finally that enhanced enzymatic efficiency or catalytic efficiency or Km by Kcat by Km has any advantage whatsoever if the reaction is going to be controlled by the diffusion rate. So there are enzymes which have reached the level inside the cell. Aconitase is a very good example where aconitase, I hope you've heard of this enzyme. I hope you know what it does. It's in the TCA cycle, where rates of reactions are as fast as could be controlled by diffusion. Okay, so this is the essential revision of the last class, and I hope you are all familiar with this and understand this argument clearly. So the fractional saturation methodology is actually significantly superior to the and the binding constant logic is far superior than the standard Briggs-Haldane formulation, because finally they end up with the same result. Now really, now let us get on to get away from sort of biochemistry and get down to some serious engineering. And from now onwards, I think we will get into serious engineering. Now, what is the biggest problem with, what are the kind of, what are enzymes used for in industry? Let us have a very simple answer. Most commonly, enzymes are used for what? Especially industrial. They're used for industrial transformations, right? Most industry would use them for industrial transformations, which cannot be done by chemical processes very easily. And the biggest problem with their substrate and their product, for example, any transformation. The simplest example I can think of where I used to work, glucose to fructose, or we were actually trying to make rare sugar fructose to something called psychose. I don't want to bore you with it. Sometime when I get a chance, I will talk about this. This is a novel rare sugar. Now, the biggest problem with this, what is the biggest problem with glucose to fructose conversion with enzymes? Can you tell me why this formulation is not good? Can you think about the glucose to fructose transformation? It is this. It is no longer this, because delta G values are small. And this is the question I keep on asking students, and they cannot, because as an engineer, therefore, you rather work with Michaelis-Menten kinetics where delta G values are close to 0. Therefore, the backward reaction becomes equally important. And somehow, for reasons unclear to me, these are not given in the text. So industrial enzyme engineering or enzyme engineering therefore starts deviating at this point from the standard textbooks of biochemistry. So what is the formulation? S plus E is Se. Now I will write this as some kind of equilibrium with Sp or Es. What the hell am I writing? Not Sp. Es, Ep, and this is actually the one and the same. And this reaction now is no longer this. It is E plus P. Got the point? All of you clear about this formulation? Hello?
Yes,
So
it's
we are
clear.
talking about reversible enzyme kinetics, reversible Michaelis-Menten kinetics, kinetics. This is the real part where it starts in more practical engineering logic. Now, how do we formulate it? Tell me. So V is now, so S going to P is now Vf minus Vr, the same way as we did with mass action kinetics. Now you understand why I was bringing in mass action kinetics and elasticities and etc. etc. So what is Vf? Forward minus V reverse. So now the enzyme is, now we do the same fractional saturation logic. What is the enzyme? Et is now equal to E free enzyme plus Es plus Ep. Do you follow this argument? Right? So, and
Yes, sir.
let us say that इसको मैं इसका डिसोसिएशन कांस्टेंट में Ks ले लेता हूं और इसका डिसोसिएशन कांस्टेंट में Kp ले लेता हूं. ठीक है ना? तो फॉर बताइए क्या होगा? Ks is equal to E into S upon Es. Yes. And Kp is E into P upon Kp. Sorry, Ep. What am I saying? Okay? Now I want to, and so we need to write V as Vf minus Vr, and V forward will be equal to some V forward max, है ना, into Es. When everything is Es. Can all of you see this?
Yes, sir.
Upon yes, sir. हाँ, Et. तो इसका बताइए क्या फॉर्मुलेशन होगा? Now I want you to do this. This is a simple, very simple algebra. Now इसका बताइए क्या फॉर्मुलेशन होगा? Using this basic material balance. So ES को लिखिए ET के टर्म्स में और ET को लिखिए E plus ES plus EP के टर्म्स में, E के टर्म्स में. Same way. Let me sort of start writing, and you people will prompt me because my algebra is very weak. So go ahead. So we write Vf is equal to Vf max something, just like Vm, but it's now V forward max, and we write Es as E into
E minus E into EP minus EP.
E into S upon Ks. ठीक है? और नीचे हम लिखते हैं E plus E into S upon Ks plus E into P upon Kp. Make sense? Yes. Okay. This is the way I did it in the last class. And then I divide by E. And if I divide by E, then I can cut out this, cut out this, cut out this, cut out this. Right? And so we get Vf is equal to Vf max S upon Ks divided by divided by 1 plus S by Ks plus P by Kp, right? Yes, sir.
Yes, sir.
And therefore, and I will now jump, and therefore I will now jump. V is equal to this is equal to VF minus VR minus क्या होगा बताइए, VR max P by Kp upon 1 plus S by Ks plus P by Kp. ठीक है ना?
Yes, sir.
Sorry for this very irritating trouble all the time. S by Ks plus P by Kp. So this is your basic Michaelis-Menten formulation now, which seems a bit irritating. And we need to simplify this because this is the formulation now, right? So ET is now dividing up into E, ES and EP. So you have a forward reaction and you have a reverse reaction, and using this basic, so fractional saturation life makes the algebra part much simpler if you use KS, KP kind of definitions. Okay, so really the one of the things that we should do, and that's very obvious, is that we should, the way to simplify this is to remember that these are also, इसको याद रखिएगा आप लोग, these are also equilibrium relationships, and so I will bring about what is called the Haldane equilibrium relations. Haldane seems to have done a lot of work, so brings Haldane equation, Haldane equilibrium relationships. And the Haldane equilibrium relationships. And Haldane equilibrium relationship is nothing but the fact that delta G is very, very small. So you would have at some point at equilibrium, what would you have at equilibrium? What would you have at equilibrium? Vf equal to Vr, right? Because the V is equal to 0. The forward and the backward reaction should be equal. So from this above equation, you can see that this will be equal to this. Correct? Hello? So what is the Haldane equilibrium relationship therefore? Can you tell me? All of you hearing?
VF
is equal to VR max P by Kp. And so this is the Haldane equilibrium relationship, which also can be simplified further. But this is only true when? This is only true when VF is equal to VR, when this S and this P are actually S equilibrium and P equilibrium respectively. These are the equilibrium concentrations, right? Which are determined by K. Remember that K equilibrium is equal to P equilibrium upon S equilibrium. Right? Is it not so?
Yes, sir.
Yes, sir.
So therefore, we can then now substitute this stuff here and get rid of this. This is, I need to be able to use the board much more efficiently. Look, you get efficiently. Can you all still hear me? Yeah.
Yes, sir.
So we have this. Now we have. So now you have this equation here, and you have this equation here, and you have this formulation here. So now tell me, what will it be? So VF, let us do it in 2 steps. So what is it? So VF, first let us substitute VF max. I'm not right max, it's obvious, right? S equilibrium upon Ks is equal to VR P equilibrium by Kp, right?
Yes, sir.
And we write therefore, and therefore this expression here, what is K equilibrium therefore equal to? K equilibrium is P upon P, so it's equal to K. Arey bhai, the hell. K equilibrium is equal to P equilibrium, which is nothing but.
So KEQ is equal to VF
KP by
into KP by KS into
KP by VR divided by KS by VA. So this equation here is called the Haldane equilibrium relationship. Okay. So essentially, the Haldane equilibrium relationship is the following, and this allows you this. Why is this important? It tells you that you cannot have this forward and backward reaction Kp and Ks any different. They are not independent of each other. They are determined and any value of Vf and Vr. So this equation tells you that all the 1, 2, 3, 4, 5 variables are all not independent. The K equilibrium fixes one of these variables. If you have a forward reaction rate which is 10 times Vr, let me write it properly so that it's obvious. What is K equilibrium equal to? Equal to Kp Vf, right? Kp Vf upon Kr, sorry, Ks Vr, right? So if Vf by Vr is, let us say, 10, let us say, so if I say that forward reaction is 10 times faster than the reverse reaction, and I know that the K equilibrium is, let us say, glucose fructose 1, 50-50, then Kp and Ks, the binding constants, will be obviously 1 upon 10. You get the argument. So you cannot sort of have a ratio of Vf by Vr as 10 and equilibrium constant of 1 and independently vary. So Kp and Ks are automatically chosen here. Their ratios also becomes 1 by 10. So this is the Haldane equilibrium relationship, and that is why it is so very useful. And using this now, can I sort of simplify my V values from this big large equation? Can I introduce from this, because we want to write it in terms of only the forward reaction. Remember what I did in mass action kinetics? I wrote Vf, V is equal to Vf minus Vr, and then I wrote it as V1 minus rho, Vf1 minus rho. Remember where rho was where gamma was the mass action ratio and rho was the disequilibrium constant. Now can you think of writing this in exactly the same way as we did the mass action kinetics in terms of rho? How far are these substrates and product concentrations, this product here and this substrate here? Can you see what I'm circling, and can you match it with my words, or is it there's a time lag? Hello? Yeah. Can you see which substrate I'm marking here? Yeah. So now tell me how we can now use the Haldane relationship, this relationship here, as it is a communication poor quality, computer poor quality, so many problems. So Haldane relationship here, this relationship here, this K equilibrium relationship here, and bring it into this expression here to simplify this expression and write in terms of forward relationship only. So really this Haldane equilibrium relationship can now be used to simplify this expression here to much more simpler version, using the same logic as I did in mass action kinetics and bringing in rho and the disequilibrium ratio and the mass action kinetics and the mass action ratio. So what do we get now? If we do this, I would be happy. So V is now equal to, बताइए क्या होगा? I want to write it. Let us be very honest here. I want to take Vf constant out. Okay. And then I want to take this as common also. 1 plus S by Ks plus P by Kp. That cannot be handled. So what is this? Vf constant ले लिया. अगर हमने बाहर ले लिया Vfr, तो अंदर क्या रहेगा? Vf max S by Ks minus, okay, let us do it like that. VR by Vm, Vf, P by Kp. ठीक है ना? अब इसको सिंप्लीफाई करिए जरा ऐसा आप लोग with the term within brackets. Let us take S out also. For example, let me take S out also. And then I have 1 by Ks minus this divided by, I've taken out S, so this divided by S. Oh, I should have written it straight line. Into S. I want you to do this on your own. Use the Haldane relationship.
To take 1 by Ks common, right?
Yeah, even better. So नीचे भी Ks ले लीजिए, Ks भी निकाल लीजिए. तो यहाँ पे S भी ले लीजिए बाहर और Ks भी बाहर ले लीजिए और यहाँ पे Ks लिख दीजिए. And also remember, so this is Vf upon Ks, and this is now, this part is now 1 minus this. So I've taken out Vf upon Ks out. This is 1 minus this, and use this equilibrium relationship and the rho values. What is rho? I hope you remember your rho.
Sigma by K equilibrium.
So gamma by K equilibrium.
Oh, yeah, sorry, gamma by K equilibrium.
And gamma was nothing but P actual upon S actual. The mass action ratio. Mass action kinetics. Now I want you to do this.
So it becomes Vf into S by Ks into 1 minus rho.
Yes. So it becomes, no, 1 minus, upon K equilibrium नहीं आएगा. Or P upon K equilibrium आ जाएगा actually, you're right.
So
1 minus
E
1.
by S upon KQ, right? So
absolutely. So shall I rub this out? This I can now rub out. And so you can now see, so now you can now see that V is now equal to Vf S upon Ks divided by 1 plus S by Ks plus P by Kp. So notice this is something like a inhibition kinetics, competitive inhibition kinetics, because I can simply divide by, I can divide by 1 by Ks and get this as the same formulation, right? Remember, where P could be replaced by inhibition kinetics, and this into 1 minus rho, and that is it.
yes, sir.
All of you can get this. Just do this. I will wait for 5 minutes.
Yes, sir.
Or is it a wrong formulation or is it a correct formulation? Because it is, or I can take V by Vf, Kf and write S minus P by K equilibrium also. But if I use this formulation here of rho, then also this is P by S upon K equilibrium, and then I can. So you can see the similarity of formulation of mass action kinetics. This is just the forward reaction. This expression here is just nothing but this. This is the same as this, and this whole, this minus this now becomes this minus into 1 minus rho. You see the advantage and the elegance of this formulation. This is a very useful formulation to have. Okay. Okay, and I want you to sort of now think about these things. So you know, now I want to now sort of get into what is, okay, is this clear now? So I will sort of, can I rub this out and go into slightly more algebra? So we have now, I'm now repeating myself. I am now repeating myself. Let us sort of revise this. That the Vf by, as I said, Vf max is equal to how much? Is nothing but S by Ks in the same formulation upon 1 plus S by Ks. And let us sort of quickly write this algebra now. P by Kp. right? And similarly, VR by VR max is also equal to P by Kp upon 1 plus S by Ks P by plus P by Kp. Right? And as I said earlier, V is equal to Vf minus Vr. And Haldane equilibrium relationship we have derived as, what did I write as Haldane equilibrium relationship? What is the Haldane relationship? I rubbed it out, so I should keep it with me. What was it? K equilibrium is equal to Vf Kp
by VR.
by Vr. I mean, you will have to go back and practice this. Otherwise, you know, you will end up in all kinds of trouble. And therefore, we derived this basic formulation of. Now, notice that I have this formulation here that velocity therefore becomes equal to Vf S, right, upon Ks. Vf S upon Ks 1 minus gamma by K equilibrium, which is nothing but rho, which is rho. 1 minus gamma by K equilibrium into S by Ks. Sorry, not S by Ks. S by Ks तो निकाल लिया, क्या कर रहा हूं मैं? 1 upon 1 plus S by Ks plus P by Kp, right? This is the essential formulation of a forward reaction. Okay. Now, what is the total saturation? So, am I? Can you understand what I'm trying to do here? What is the total saturation? The total saturation is this S by Ks upon 1 plus S by Ks plus P by Kp, right? This is the for the forward plus, of course, plus of course, can all of you hear me? P by Kp upon,
yes, sir,
1, there's a lot of writing stuff which I don't like, plus P by Kp. This is the total saturation, right?
yes, sir,
Isn't it? So this total saturation is nothing but Vf upon Vf max, and so this kind of algebra you should do, plus Vr upon Vr max. Isn't it? And notice that the numerator is always less than the denominator. So this numerator here, this is what I was trying to point out, that this numerator here, this is the total saturation. This numerator here, because this is the denominator, 1 plus this, is always less than the denominator.
yes, sir.
Right. Therefore, by definition, total saturation, this total saturation here will always be less than 1. And each of these is also independently less than 1. Of course, this is also less than 1. This is also less than 1.
It should be less than
Okay.
2, right? Because we can't say that these are less than half each of them.
No, I'm not saying that. I'm saying less than 1. But together also they're less than 1. Because if you add them up, they're less than 1.
Okay. Yeah,
It,
yeah,
right.
right.
Plus this upon this. So together they're less than 1. Individually they're less than 1. I am not saying that both are less than half. If this is 0.75, then by definition, P by Kp, this fraction will be less than 0.25. Right?
Yes,
Are
sir.
you getting this? This is very obvious. Yeah. I mean, yeah, think about it for a second. And so there, and each is less than 1, and therefore, you know, usually S is significantly larger than Ks, and if, no, sorry, I'm not making that argument. I'm saying, let us assume, let us say that the substrate that you have added is very, very higher compared to Ks, just like in Michaelis-Menten kinetics, and we were getting 0th order reaction. Now, we would earlier in Michaelis-Menten kinetics, when S was much, much larger than Ks, what would we say? We said fractional saturation was equal to 1. Remember? But now it is no longer proof that when S is much, much larger than Ks, we have fractional saturation equal to 1. Because to make fractional saturation equal to 1, you would also need P to be much, much larger than Kp. Only when both these numbers are very, very large, you would have a situation where the fractional saturation approaches 1 instead of tends to 1. Oh. So I'm trying to make a conceptual point here. Fractional saturation earlier tended to 1 in Michaelis-Menten kinetics the moment S was much larger than Ks. Remember, fractional saturation was S upon. Can you hear me, all of you?
Yes, sir.
Yeah. So earlier in Michaelis-Menten, ordinary Michaelis-Menten kinetics, the requirement for fractional saturation approaching 1 was simply given by this, or rather this implied this, because S was much larger than Ks. Now the fact that S is much, much larger than Ks is no longer a necessary and it is a necessary condition, but it's not a sufficient condition anymore that fractional saturation will approach 1. For fractional saturation to approach 1, both S has to be much greater than Ks as well as P has to be much, much greater than Kp. That is all I'm trying to say. Now, okay, we are running out of time. Okay, so I leave it for you now, this very simple exercise, that what is the elasticity? What is elasticity? So EVF, independently maybe you should do with respect to S, and EVR with respect to S, and the fact that now you have close to thermodynamic equilibrium, what is the situation and how will you handle it? Because now you can use the 1 minus rho formulation to find out. Remember, I did the same thing for mass action kinetics, exactly the same way. You try to do it for this and try to find out elasticities as a function of the kinetics as well as of the thermodynamic equilibrium. Or in the next class, we will sit and do this. Is this problem clear?
So could you repeat it once?
I'm saying, now tell me what is EV by S? Simple. Or you can find out, because V is equal to VF minus VR. So because this is then irritating business. So what is EVF by S? And what is EVR by S? Right? So we want to know the elasticity of this equation, and then we will be able to handle this when it is close to equilibrium and far from equilibrium. So now it is no longer just the Ks values that are important. Remember, earlier V by S was a simple form function. What was it? Km upon Km plus S. So the substrate concentration essentially determined the elasticity. Simple. So the substrate concentration, when it was small, when S is small, very small, and then EV by S was EV by S was equal to 1. When S was large, it was equal to 0. Now it is a matter of how close to equilibrium it is, just like your mass action kinetics. So now remember, I did mass action kinetics. I did V is equal to K1A minus K2B. You forgotten or you remember this?
Yes,
I did the elasticity. Yeah, so in exactly similar ways, now you have a more complex problem of elasticity at close to thermodynamic equilibrium. And this becomes very important in industry because we are trying to look at conversion rates and we want to convert the full glucose to fructose as close to equilibrium as possible. Now, what happens when industrial fluctuations take place? How does the output concentration change? How does the velocity change? These are why these things become important. So we'll stop here, and I want you to find out the velocity, using the basic equation that I've given you and the basic rules for elasticity finding. I want you to find out the elasticity of the reaction with respect to substrate, the forward and the reverse reaction, and what happens when they're far from equilibrium and what happens when they're close to equilibrium. Okay? Let us stop here.
Yes, sir.
Any questions? And you followed this. Is the pace okay, or can I increase the pace, or I should keep it the same, or I should reduce it? Is the pace of teaching?
I guess it's fine, or maybe you could increase it a bit. Like, but
We can increase it a bit.
if
Oh,
others,
thank you. थोड़ा मतलब मैं धीरे चल रहा था because many students sort of tend to complain that आप slowly चलिए, आराम से समझ में आने दें. So I can increase it slightly. Okay, thank you.
yes. So one more thing, sir, could you provide us with some practice questions for like?
Yeah,
these?
practice questions and the book. Yes, tomorrow I will upload the book, one book that I managed to locate, which has these things. A very simple book. I will upload a complex book as well as a simple book. You can go through the simple one first, and those of you who are interested can go through the more complex one. And there is an even more complex one which I am not uploading, Cornish and Borden, which is the more standard textbook of enzyme kinetics. But that is because I want to shift to the engineering aspects and not remain a biochemist in terms of enzyme kinetics. I want to shift to, things like PFR and CSTR and immobilization kinetics and mass transfer coupled with kinetics and stuff like that. I want to shift into that aspect rather than go on and on about boring enzyme kinetics. I mean, because enzyme kinetics can become very, very, very complicated. Biochemists have had algebraic Hahnemann equations and all that. Those are very, very tedious. I don't want to get into that. I would rather do this on a more engineering side. So thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.